Okay. Okay, so yesterday we didn't finish the foliation theorem in the parallelizable case, so we will begin with finishing it. Seemingly, we have not even finished the case of codimension 1 in dimension 3, which is far from being general, but in fact, we've introduced all the ideas for the general cases. So let's quickly finish to understand this way to construct foliations of codimension 1 and 3 manifolds. We were in the case equals 1 and 3. So foliations by planes on 3 manifolds. And we had so a 3 manifold. In the beginning, we had a plane field which is not integrable, but which is transversely orientable, since we are in the parallelizable case. The normal bundle, which is here a real line bundle, is trivial. So, and we have managed to realize it by a foliation. I mean, after a homotopy to make it tangential to a foliation by surfaces, except that we had some pairs of critical points and we have changed them to holes. So we have a large part of M3 is already foliated, but there remains some holes which are just like what I called the standard straight hole, that is D2 cross I, with the foliation being tangential to the top and the bottom disks, and on the vertical boundary, we see the suspension of the diffeomorphism of the interval, which is unfortunately not the identity. So none of these holes is fillable, unfortunately. So the next step is to round the holes, because you remember that if we have a hole like this, but with S1 instead of the interval, then after Thurston's methods, we can fill it with 2 grade components inside. So we want to round the holes, and after Thurston's nice idea, well, so outside of the holes, it's already foliated. If by chance we can find in the foliation a transverse path, say the foliation is a transverse path from the top of the hole to the bottom of the hole, then we can take a worm, and the worm will dig his gallery, eating his food in the foliated part, and go from the top to the bottom. And then, of course, after the gallery of the little worm is a small neighborhood with trivial foliation. Small neighborhood of this path with trivial foliation, a thin solid cylinder, and if we round the holes, then if we round the corners, then we find a round standard hole with monodromy given by phi on one half of the circle and the identity of the other half of the circle, but it's a perfect diffeomorphism of the circle, and so we can fill it. unfortunately, it is not true contrarily to the contact case. In a codimension 1 foliation, it is not true in general that given 2 points, you can find a transverse path between them. So instead, we have a little theory, which is very quickly understood due to no difference, but it is very elementary, of accessible points. So I'm thinking of M minus the whole, and I have a codimension 1 foliation F, and I choose 1 point, which is maybe this one or slightly above this one, from A. And I say that another point X is accessible if and only if there is a transverse positive path, because F is transversely oriented. From A to X, like this. So the little lemma is that the set of accessible points is saturated. It means that it is a union of leaves, and its topological boundary, the large A, its topological boundary in M is a union of compact leaves. So let's verify these 2 very elementary facts. Saturated is really clear. But if I can go to X by a transverse positive path, and if I have a X prime in the same leaf as X, of course I can do this, and then continue to be transverse, almost parallel to the leaf, to go to X prime. And so the topological boundary is also saturated, also a union of leaves. I claim that all the leaves in the topological boundary are compact. And this is also very easy, namely by contradiction. Assume that you have a leaf in the topological boundary which is non-compact. It means that you have L, let's go upon X, and some points arbitrarily close to X, you have accessible points and non-accessible points. And it is saturated. So necessarily, you have infinitely many non-accessible points. Where are they? Below X. And you have an infinite sequence converging to X from above of accessible points, like a wide N. Right? From A, I can access these points, but not those ones. And X, I don't know. It is not important. So now, by contradiction, assume that L is not compact, so it has to accumulate somewhere in the. It has to accumulate to some point, say B, somewhere in the manifold, from above or from below or both. But anyway, something is obvious. If I take a small transversal through B, then the leaf L has to meet it at least twice. But that's not possible because since the sets of accessible and not accessible points are saturated, necessarily here I find all the leaps with the x n's after some large n. So here I have many not accessible points. And in the same time, here I find some the leaves which are through the y ends. So those ones are accessible, but from an accessible point here to an accessible point. It makes a contradiction. Okay. So this shows the lemma. And so say Thurston. Well, unfortunately, there are some compact leaves, but let us destroy all of them. How do we destroy all of them? We make more holes. Every time we see a compact leaf, we choose two cylinders like this, and we make this gate transformation between these two pillars. That is just changing the horizontal foliation to one which put the points a little lower, using a diffeomorphism of the vertical interval, so as to introduce some monodromy here, two new holes with monodromy, and between them, the leaf that was compact now will contain in its boundary one of these infinite spirals, so it's not compact anymore. And in fact, if I put a lot of, if I make these things in a lot of places almost dense with the manifold, then I can be sure that every leaf meets one of these spirals, and so no leaf is compact. And so the set of accessible points from any point is the whole m minus the holes. And so all of these holes, the old ones and the new ones, admit worm galleries. Of course, I can make them 2 by 2 disjoint. And so everybody becomes round holes, and I can fill them. So this was one of Thurston's methods to produce 3 manifolds. Okay. Now, I would like to say a brief word of, and it will be necessary for the following anyway, to the case, still the case of codimension 1, but now for ambient manifolds at least of dimension at least 4. There is a part of what we have said for dimension 3 is almost identical for higher dimensions. Recall, so we have a manifold of large dimension. We get wrinkles of codimension 1, so there are pairs now of critical points of singularities, pairs of singularities of some index S and S plus 1, with S between 0 and n minus 1. So the serious cases are S between 1 and n minus 2. And I claim also that we can cancel such wrinkle by change it to a hole. Namely, recall the figure that we had. So we take two small disks, which are the germs of the unstable manifold here and the stable manifold there from some local pseudo-gradient. So this disk D is of dimension S plus 1. The pseudo-gradient is descending. So this is the unstable disk of C prime, which is of dimension S plus 1, call it D prime, and that one, the stable disk of C, is of dimension n minus 1, n minus S, right? And so here they are. Recall that we consider the part of this gradient line between the two disks. So above we see this small part of the disk D prime, there a small part of the disk D. You should think to the boundaries, and in projection to in horizontal projection, this will give the R to the S, the projection of the boundary of D prime, and the R to the n minus S minus 1, the projection of the boundary of D. And so we should rather think to this disk there. This is a disk of dimension S. That is a disk of dimension n minus 1. That is the product of the two disks. And the corners here are the products of the two spheres, S to the S minus 1 cross S to the n minus S minus 2. Say sigma for a B sphere, product of two spheres. And we can do just the same as we did in dimension 3. So we take a small neighborhood of the B sphere, which will be a sigma cross D2, because it is of codimension 2 in the horizontal hyperplane, and dig the pillars. And so these pillars are, and so the hole that appears is a sigma cross D2 cross I. And we can do just like before, kind of gate transformation, and it will leave a hole of this kind, which we should think as this standard straight hole, somehow stabilized by sigma. This means just think to this hole, think to the sigma factor, it's a closed manifold. So when you make the product, the boundary of the product is just the pre-image of that, the product of this boundary by sigma with the pullback foliation, and you have to fill it. So in codimension 1, this filling works. It's due to Thurston and is very technical. Because the idea is that you can also play the game of worm galleries, and you will do it. But now the worm gallery is very small with respect to the topology of the whole. So, and it is the liberty that the freedom which is given with respect to the REB global stability theorem lies in this very tiny worm gallery. And so it is really very technical to understand how you can fill the hole, but you can first unpick it. And we will not do it now. In a more interesting way, we shall pass to the...
Would it be easy to fill if the diffeomorphism was somehow supported in like a very tiny ball? Would it then be easier to fill?
Sorry?
So there's going to be some kind of diffeomorphism that gives you the foliation on the boundary.
Yeah.
If it's in like a tiny ball, is it easier to fill it in?
You can think like this. Sigma is here.
Yeah.
This circle represents sigma. It's a little philosophical. That interval represents D2. The interval here represents D2. And so the standard straight hole is here with the suspension of the diffeomorphism as that spirals like this, and it is stabilized by product by sigma. And as if there were only that, it would not be fillable by Rape's global stability theorem. And you have this liberty of a small gallery, and Thurston's methods will make fill it, but
So
very
on
complicated.
the boundary is
Very
somehow,
complicated.
let's do with a diffeomorphism of what's on the boundary has to do with a diffeomorphism of sigma times an interval. It's like
It's trivial sigma family of
Yes,
diffeomorphisms of the interval.
yeah, and even the diffeomorphism will be the same. The same for each slice. And so when you complete it this way, it is not a round hole times sigma. You have much less room to work.
And I mean, why does rave stability apply? Because I mean, you could have like, I mean, it may not be simply connected.
At least when sigma is simply connected,
Okay,
it does. Anyway, it does.
Yeah, okay.
It does in all cases. So you can verify that this is not fillable without
does the proof use fragmentation for diffeomorphisms?
It does, to my eyes, it is not linked with fragmentation. You will use the decomposition of the diffeomorphism into rotation and a conjugate of the rotation. And seemingly we use this difficult theorem of Hermann. But in fact, we never, because if you remember the choice of phi, it just had to send some point of the interval to some other point of the interval. So you can always arrange that it is already in the Hermann form in an elementary way. Okay. So let's pass to another dimension. So let's remember the general wrinkle as Kai explained to us. So take a wrinkle. So now consider a wrinkle of some index S. 0 and P minus 1. We have I try to have the same. So we have coordinates z. X1, xp. And y1, yq minus 1. This is supposed to be r to the n. And I think also of the image in r to the cube. And remember the wrinkle. Map. So the y's, y1, yq, z, x1, xp will be sent. So the y coordinates are unchanged. Sorry, y to the cube minus the y coordinates are unchanged, and the z coordinate is sent to v3 minus 3 norm of y squared minus 1, probably plus 3, plus q of x, where q is a standard quadratic form of index S. And remember that the critical set sorry, there are two sigmas which have nothing to do with each other. The critical set sigma is just the unit sphere in the YZ plane and image. Okay. So I claim that we have done everything to change this to a foliation locally. And it's easier than in codimension 1 because the whole will somehow be rounded easily in a small neighborhood of the wrinkle. You don't need these global things that you meet in codimension 1. Namely, take some value of y with norm less than 1 will correspond to this vertical slice, y equals constant. Which is mapped wow. So W restricted to this slice y equals constant, you see exactly r to the p plus 1 with one-dimensional wrinkle, with a one codimensional wrinkle. Two critical points of index S and S plus 1. Restriction to this. So we shall apply what we did in codimension 1 in a parametrical way for all these y's the square is less than 1. And we have to think of what we do when we arrive close to the cuspidal points, the birthplace points, well, then we apply exactly the Thurston flexibility trick. You remember this one parametric family of fillings. It's exactly the tool that we need to make the junction between these the constructions for y for normal y less than 1 and between normal 1 less than 1 and normal 1 a little more than 1. So we cancel the two singular points in each slice, and in each slice it gives us a hole, a part which remains unfoliated, and all these holes considered together make a big hole. What is this big hole? It's just the collection of all the small holes. So the big hole also had the form sigma cross d to the q minus 1. This is a big disk. Cross I. Is that it? Are the dimensions good? Sigma is of dimension Q. No, sigma is, sorry, not the same. The sigma is of dimension. That one is of dimension. It is written. N minus 3, but this n was the dimension of the slice here, so it was p plus 1. But it could be the dimension p minus 2, if I'm correct. P plus so this sigma is S to the S minus 1 cross S to the n, but this n is P plus 1. Minus, n minus S minus 1. Yeah, okay. Sorry. I think it's kind of, so it is a dimension. Am I correct? The dimension is p minus 2, q minus 1. Sorry, that's the 2 of course. The base of the base. No. And we can, and in fact, it has the following form. Naturally, it's a kind of straight hole, but it's the sigma stabilization of a kind of straight hole, but whose vertical, instead of the interval, is now the interval cross d to the q minus 1. And this parametric family of monodromies that we have made make a global diffeomorphism of I cross the q minus 1, and which has a very specific form because it comes from all these slices together. Namely, here is d to the q minus 1. There is the interval, and it preserves every vertical segment. And it is compactly supported. I claim that this hole is easily fillable. For I cross dq minus 1, this is the vertical here, and large phi is such a diffeomorphism of this product. So since it is completely supported, the support is contained into some slightly smaller product like this, and it is the identity on the complement. But you can think of this not as a dq minus 1 cross. This dq minus 1 cross I can be actually contained in a dq minus 1 cross S1. And you can think of phi as a diffeomorphism of dq minus 1 cross S1, preserving every S1 fiber. So it's actually a parametric family of round holes. So since we know how to fill the three-dimensional round holes with S1 cross D2 parametrically using Thurston's flexibility trick, it gives us a recipe to fill this hole, and we just have then to stabilize by the this field. Very direct. Okay, so this finishes the proof of the foliation theorem in the parallelism case. I would like to speak of the general foliation theorem of Heffliger structures and of P gamma, which are everything that permits to solve partly the fundamental question in the non-parameterizable cases. The idea of a Heffliger structure is very natural. If you think of the following problem, what is naturally the fullback of a foliation? So think to a foliated manifold, the M, another manifold, M, and a smooth map from M to N. Of course, if it is transverse to the foliation, then the pullback will be a foliation in M. But what if it is not transverse to the foliation? Somehow tangential to the foliation at some points. So if you think that the foliation, if you try to understand what kind of singularity can happen, just think that the foliation is locally given by submersion to RQ, which is of codimension Q. So actually, locally, the singularities of the pullback will be any kind of singularity of a mapping to of a smooth mapping to RQ. But it is possible to make a regular object by the tool that the trick that we have already encountered of micro extension. Namely, the foliation F has a normal bundle and first pull back this normal bundle as a trivial as an abstract bundle over M. So, and think to a small disk, a small disk in a fiber center that is at 0 in a fiber of this pullback bundle. So it is sent isomorphically, diffeomorphically to the if you take, for example, an auxiliary Riemannian metric, you can use the exponential of this metric, and this disk by the exponential in the direction orthogonal to the foliation is sent to a small disk which is transverse to F. So this means that you get mapping into N, which is transverse to the foliation. So in a small neighborhood of the 0 section, in the pullback bundle, you have a mapping to M which is transverse to F. So you get a pullback foliation. And this pullback foliation is not only regular, it is also transverse to the fibers. So that's a technical structure. Let us read the definition. The Hefliger structure of codimension Q. So
Why fibers?
Sorry?
Not transverse to the fibers everywhere, is it?
Yes, it is transverse to the fibers. Well, I mean, in a neighborhood of the 0 section. Yeah. Precisely, the Hefliger structure or gamma of codimension Q or gamma Q structure is a pair of a bundle and what we call a microfoliation, where nu is so over manifolds M is where nu is a vector bundle of rank Q over M, which we call the normal bundle. And we call it the normal bundle, but in this setting, it is not normal to anything. It is an abstract bundle of rank G over M. And round M, the microfoliation is a germ of foliation of codimension Q on some open neighborhood in the total space E of the zero section, which is transverse to the fibers of top. This is the total space of the bundle nu, and so on some smaller open neighborhood of the zero section, you have a foliation which is of codimension Q and transverse to all fibers. So the leads have the same dimension as M and are E-tail above M. And the position with respect to the zero section is arbitrary. It is not necessarily transverse. And precisely the points where it is not transverse are the singularities of the Hefliger structure. So it is in some way the good notion of singular foliation. At what time did I begin?
40, if I recall correctly.
Yeah.
Sorry, at 40. And so the general prediction theorem is as follows. Let M be a manifold. Gamma be a reflex, so Xi be a codimension Q plane field on M, and gamma is a Hefliger structure of codimension Q over M, such that you have isomorphism between the two normal bundles. You have two normal bundles, the one of the plane field which is the quotient of tau M by Xi, and the normal bundle to gamma. Isomorphism of vector bundle. Then there exists a foliation on M of codimension Q, such that the tangent field to F, that is F regarded as an integrable plane field, is homotopically Xi. And the foliation regarded as a Hepliger structure is concordant to gamma. And then I should. So in particular, I will give so this is the general foliation theorem. So to get to answer for a positive answer to the fundamental question, you need the plane field is not enough. You need also a microfoliation on the normal bundle. There exists C prime homotopic to C, which is integrable. If and only if the normal bundle 2m over C admits a microfoliation. And of course, we understand that in the case where the normal bundle is trivial, then you have the stupid microfoliation, which is horizontal. So this is what we do. And let's give the proof. Of the theorem. Well, practically already done. We have already the ingredient. So we are given the plane field C, and on the bundle normal to C, a microfoliation. I claim that we have the formal data for a map from M to the open neighborhood of the zero section transverse to the microfoliation. Because at every point of M, so think to, this is the tangent bundle to M at X. And that is the normal, this fiber is also 2xm divided by xc of x, the quotient. So you have an epimorphism from this to that. That is a subspace of the tangent space to this neighborhood of the zero section. So we have exactly a formal with Z together with D. This is the formal data for a mapping from to this neighborhood, which is whose image of the formal differential is the fiber that's transverse to M. So if M is open, we are done by the Gromov open invariant open relation H principle. We have a mapping from M into this neighborhood, which is transverse to M, and we just have to pull back the microfoliation. If M is closed, then as Kai explained to us, we don't have such a map, but we have a map which will be somehow wrinkled with respect to the microfoliation M. Something, maybe we can even arrange that it is.
When you say map, do you mean an immersion or an embedding or?
It's not very important here.
We've got to pull back the foliation. It better be immersion.
You can certainly. I guess that you can make it section, but it's not very important. Even if it's a smooth map, not an immersion. It will even a smooth map will work. Anyway, this map will be a smooth map which is not close to the zero section will work because it is homotopic to the zero section.
I mean, definitely in the first case, it's graphical, right? Because you're doing kind of holonomic. I mean, you're following some tangential rotation to make it transverse.
You don't have the data that's in the rotation.
No, that's what you're about.
So you get
This one will make it.
a map which is somehow transverse to the in most places transverse to the microfoliation, except for some wrinkles. Somehow, but so if I zoom on such a thing, I see a wrinkle. Here is M. And these wrinkles, you can also arrange that they are very small. So they are contained in places where the microfoliation is given by a submersion, the projection, the local projection to the fiber. So actually, you get an M something which is a foliation, except for some places where it is wrinkled, but in these places it is locally defined by a submersion. So you can apply the wrinkle cancellation that we did. You know, and change all these wrinkles to foliations. So I want to say that so this theorem is due to Gromov, Phillips, Heffliger at the end of the 60s for open manifolds. So Thurston extended it to closed manifolds in the 70s with methods which are not at all like this. He didn't have the wrinkles, and his methods were very different. And the method by the wrinkles is due to Elias Bagnichev in the wrinkles trilogy in the 90s. And I followed their method, except for the details of the filling the holes and of the replacement for the wrinkles by foliations, which they have something analogous, but I think that this one is really natural. So I haven't explained two things that I wanted to explain. First of all, why two-plane fields are always homotopic to integrable ones, to smooth integrable ones. It's due to the topology of the classifying space for Heidegger structures. And the second is the Mather-Thurston theorem, which gives a deep relation between the homology of this classifying space and the homologies of, say, the diffeomorphism groups made discrete. And the interest to speak of it in such a summer school would have been that there are several ways to prove the Mather-Thurston theorem, and some of them are also deeply linked with H principle and rank. Thank you.